Hello everybody, this is Stereo Police, and welcome to Lecture 3, Resistance and Resistors. And I really feel that this is one of the more important foundational lectures. And as I mentioned previously, everything builds from the previous, and we're working from the specific to the general. And I'm not going to be talking too specifically about audio equipment today, except for one particular image I'm about to show you. But in some of the subsequent lectures, I'm going to start to relate more and more to audio equipment. But we absolutely need to build on this foundation. And resistors are just absolutely ubiquitous. They're everywhere. Without resistors, there would be nothing. We wouldn't have audio equipment. They're everywhere. I haven't really thought about it, but I think it's probably one of the most common components you see when you look at a circuit board. Let's take a quick peek at a circuit board. And this is an old school kind of circuit board. Not one of those modern surface mount boards. It's kind of hard to tell what anything is. But as you can see, I've highlighted some resistors. And you've probably seen these quite often, here and there. Again, surface mount components are very challenging to identify. But these old school carbon resistors are rather easy to identify because they have color codes. And they come in different sizes. And typically the larger sizes are higher wattage resistors. They're capable of higher powers. There's tiny little 1/8 watt, 1/4 watt, and then larger 1/2 watt, and then there's some larger power resistors. But we don't really need to talk about that today. We want to talk about the concept of what a resistor does. Before we get into that, let's take a quick look at, let me go down to my bench and let's create a resistor. Let's make one and measure its resistance. And then we'll get back to what a resistor does, how it works, and the theory of it. Alright, let's attempt to make, let's just do 2 resistors with a pencil from Home Depot and a piece of paper. One resistor. And there's a second resistor. And the only difference between the two is essentially their length. And we're using a pencil, I'm assuming is graphite. Alright, let's see if we can measure the resistance using a digital voltmeter. I had that on there. So I have that, sorry. Difference in length using graphite. Alright, I've attached a couple of alligators, which go to positive and negative probes that lead to a digital voltmeter that is in the 20 mega ohm range, and we're reading that resistor to be almost exactly 1 mega ohm. So I've made a 1 mega ohm resistor. What would we expect the longer one to be? Well, there's more material in between, so I'd expect that longer one to be considerably more than 1 mega ohm. Let's check it out. Here we are, the alligators are there, and by the way, all the voltmeter is doing is passing a current right on through that graphite, and knowing the voltage and the current, running Ohm's law to figure out that resistance. Let's see what the volt, whoops, I've got a bad connection, hang on just a second. There we go, I had a little tear in the paper there. I had an open circuit. Alright, let's see. So we have a longer material should have more resistance, and in this case we've created a 6.8 mega ohm resistor. So you can tell the difference between our 1 mega ohm resistor on the left and our 6 mega ohm resistor on the right. Let's get back to the lecture. All right, returning to the lecture. Now, hearkening back to some previous material, remembering that voltage is a pressure that's going to cause charge to flow. And what resistance is a resistance to that flow of charge. There can be a high resistance, a low resistance, and anything in between. No resistance is considered a short circuit, and complete opposition is considered an open circuit. And you know, we could always return to the water analogy. Take a look at this. Just go ahead and stare at this for a second. Now remember, when we elevate a bucket of water, we've created pressure, we've created a source of potential energy. That creates pressure, water pressure. And if we opened a valve, water will flow. And depending, for example, on the diameter of the pipe, there will be more or less resistance to that flow. So here we have a lower resistance to the flow, and here we have a higher resistance to the flow. Here we have more flow analogized to more current, and here we have less flow analogized to less current. And if you want to think of it in terms of a wire, you can kind of think of it in terms of a pinch in the wire, although that's not exactly what's going on. Now, resistance in an electrical circuit is a measure of the opposition to the flow of current. And I'm going to say current from here on out, but it's the flow of charge, the flow of current. You could say it's the flow of the electron drift. And it's measured in ohms, typically symbolized by the Greek letter omega. And anytime we have an electrical circuit, we typically have a source of a supply of power of some kind. Could be AC, could be DC. And we typically have some kind of load out here. And that load could be anything. It could be a motor, could be a light bulb, could be your loudspeaker. It could be any component you can think of. It could be a resistor. But the load will resist the flow of current. It's going to limit the flow of current. If it didn't, you'd have a short circuit. And we don't want short circuits. And this is a depiction of a short circuit. And if you had a short circuit, extremely high amount of current would flow and it would destroy things. Now, of course, an open circuit exists when there's no connection between the positive, for example, the positive and negative terminals of your battery. And if you have an open circuit, you don't have a circuit at all. And no current can flow. Now, resistors, being one of the most common components, you can see here there's a bunch of different varieties. And this is a power resistor right here. And they're formed of different materials, different varieties. They have different wattages to handle different amounts of power. And again, they're characterized in ohms. And they're not polarized. They don't have negative and positive sides. You can pass current through them in either direction. Doesn't matter which side the voltage source is on, unlike certain capacitors that we talked about. Now, in terms of how they work, and let's just picture electron drift for a moment. And if you remember, harken back to a few lectures ago where we talked about the electrons just drifting, or we could think about it in terms of charge too, in a copper wire. Well, this would be analogized down here in the copper wire to a short circuit. And just all the possible charge or electron drift is flowing that could possibly flow. But the resistor is going to limit that flow. And it does so based on a mixture of materials in here that's going to convert the electrical energy into heat. So it's going to convert it into heat. So if you remember, let's say we have source of voltage out here, and here's our negative side, and we had potential energy here. We are going to dissipate that potential energy into heat. And some of that voltage here is going to be dropped across that resistor. It's going to be lost. And it does so because of the atomic structure inside the resistor. It's going to be a series of collisions. And you could analogize that to where you're just, walking in a straight line. You're in New York City, you're walking in a straight line. Everything is fine, you're going as fast as you can, then all of a sudden you experience a crowd of random people. And in order to make your way through that crowd, you've got to zigzag. And you've got to expend a lot more energy to get from point A to point B. And one thing to keep in mind, though, this is kind of an aside. And this has to do with voltage drop. I wish I had made this slide larger. In a series circuit, and these are series circuits, the same amount of current will always flow in this wire. The current can't disappear. But there's one source of potential right here. And this 9 volts, this potential, will be dropped, dissipated in heat. In this case, we have one resistor right here. It's going to be dropped, all of it, across that resistor, dissipated. That's the load. So that 9 volts will be dropped across that resistor, because when the current reaches the negative terminal, the voltage here is going to be 0. That's 0. Here it's 9. Okay? Here the voltage is 9. Here it's got to be 0. So all of it's going to be dropped. Now if we introduce 3 resistors, the same thing is going to happen, but that 9 volt has to be dissipated by all 3. So that voltage drop is going to be shared by all 3. So each of these resistors is going to drop a portion of that voltage. But nevertheless, the current has to stay the same. So in order to do that, the fact that these resistors are in series, okay, here we had a 500, and here's our 500, but we added another 500 and another 500. So we've increased the resistance of the circuit. The 3 times the resistance. So it's going to limit that current to 1/3 of the current that's in this circuit right here. A little too deep, maybe. Don't really need to know that, but I thought it would be interesting. Now let's take a look at a couple of examples and look at Ohm's law. We talked about Ohm's law, and we're not going to go that deep. But this is simple math, and I think it's really, really important to understand. And again, don't get concerned. This is a really important foundational basis as we move from the specific to the general. So let's look at a circuit with a source of 1,000 volts. Not that these are necessarily realistic numbers, but they're easy to work with mathematically. All right, so we have a source of 1,000 volts. This is a battery, symbol for a battery. Let's say we have a resistor out here that's 100 ohms. That's going to resist our flow of current. And these are our Ohm's law equations. Very simple. Division and multiplication. So what if I asked you, given these parameters, how much current is going to be flowing in this circuit in amperes? All right, how much current will flow through that resistor, which will be the same current that flows everywhere because it's a series circuit. Now, we know from Ohm's law that I equals the voltage drop across that resistor divided by the resistance of that resistor, and we know that. And we also know that the voltage drop across that resistor has to equal the voltage source. It has nowhere else to go. So in this case, the voltage drop is going to be 1,000. The resistance is 100. So 1,000 divided by 100. It's going to be 10 amperes. 10 amps will flow through that circuit. Now, in like kind, if we were to, knowing the voltage, and if we were to measure the current with if we had an ammeter up here and we measured the current, we would measure 10 amps, And if we were to calculate the voltage drop, it would be V equals I times R. So it would be 10 amps times 100 volts. It would be 1,000 volts. That would be the voltage drop. It has to be. There's no other resistor in this circuit to drop the voltage. And we're going to assume that the resistance of the wires is 0, although wires always have a little bit of resistance. All right, let's look at another scenario where we've increased the resistance. Okay, here we had 100 ohms. Let's increase the resistance to 1,000 ohms. And the example here is what happens to the current if we increase the resistance. Well, intuitively, if we increase the resistance, the current should go down, because we've increased the resistance to the flow of current. And I'm not going to prolong this point, but let's run Ohm's law. And voltage divided by resistance, 1,000 divided by 1,000 will give you 1 amp. Well, of course, we've increased the resistance by tenfold from 100 ohms to 1,000 ohms. So the current went down by tenfold, from 10 amps to 1 amp. It's a proportional relationship. All right, let's look at a short circuit. Well, a short circuit would be if I attached a wire from here to there. And, you know, we don't want short circuits, but they do happen in life. And in reality, a short circuit would be 0 resistance, but in reality, there's always some resistance of these wires. Very, very minuscule. But it's there. So there's really no such thing as 0 resistance. So I'm going to run a very small number of ohms. All right, so I'm going to take our 1,000 volt source and divide it by a very small resistance, and I get a very, very high current. And that's why if you short something, you see an arc or a spark. That's the ionization of air. Let's, in opposite kind, let's look at an open circuit. Well, in an open circuit, current can't flow. So if current can't flow, we have the voltage of the source. There's no current, can't flow. So all of that voltage will appear right here. It's just like measuring the voltage here. It's going to be the same here, and even right there. Even right here. And no current's going to flow. It would be like, and this is kind of unrealistic, we don't divide by infinity really, although in calculus there's things we can do, but it would be like saying 1,000 voltage current is voltage divided by resistance. It would be like 1,000 divided by infinity, which would lend itself to 0 amps of current, if you want to look at it that way. Okay. Now, resistance of a material, any material, is directly proportional to the length of the material, and we saw that with my demonstration earlier. So the longer material would have a higher resistance because the charge carriers have to flow through a longer length. It's inversely proportional to the cross section. So if the cross section is bigger, there's less resistance. If you remember our discussion of charge, well, there's more charge that can exit in that given cross section. Less resistance. And also, depends on the nature of the material. Some materials, by nature, such as copper and silver and gold, are highly conductive. Some materials by nature are insulators, like rubber. So it depends on the nature of the material. Also depends on the temperature. As the temperature goes up, the resistance goes up. All right, and so these are the main factors. And this is a nice little example. I'll tell you what, let me take a break right now. I'll be right back, get a glass of water, and we'll carry on with the nature of these materials. And I have a nice demonstration on my workbench. And I think you're going to really appreciate that. Returning. All right, materials are characterized by their resistivity, and actually, if you wanted to skip this slide and this slide and just carry right on, you could. I just think this is interesting. And here's a list of materials, and copper, of course, we all know copper from copper wires, is really the most common type of conductor we use out there, although as in the audio world we often prefer gold-plated connectors. Most commonly because gold is less susceptible to corrosion and thus makes a better connector over the long term. But gold is not as good a conductor as copper. As you can see, we have these materials characterized by their resistivity, meaning, as you can see from this chart, we go from the lowest resistance per unit meter to up to the higher resistance. And we go from conductors all the way up to insulators and everything in between. I should insulators. And I'm not drawing an I for current. And conductors. Silver actually is a better conductor than copper. But copper is less expensive, and silver has other properties that make it not quite as durable as copper. Now, as we get down here to some of the insulators, we can see things such as rubber, Teflon, glass, that sort of thing. Interestingly, the reason I have this slide is to demonstrate that different atomic structures of the same atom make a big difference. Now, carbon as an atom, just as an atom, doesn't have any valence electrons, if you harken back. But if you arrange it structurally, such as, and I'm hesitant to get into any more detail than this, but I want to demonstrate that if you put it in sort of a matrix form, so carbon in what's called a graphene form, shown right here. Okay, here we have graphite, but if you put it in a graphene form, it can be a very good conductor. We get into superconductivity when we talk about that. if you put it into a graphite form, we have these beautiful layers of graphene, and you can see how they can slide off of each other. Sort of the layers are not connected, and that's why graphite pencils are so nice. And here we have graphite. So, and also relative to conductivity, graphene can be a very good conductor. You just saw me use graphite to make a resistor, so that becomes a conductor somewhere in between. Whereas carbon, when it becomes a diamond, is a poor conductor, becomes an insulator. And if we look at the atomic structure of a diamond, it's very different. So carbon in different forms, structurally, as a molecule, can be very different in terms of conductivity or resistivity. Interesting. Now let's get into the carbon resistor. We're not too far away from the end here. And this is what we looked at the very beginning. There are many forms of resistors and many different materials that can be used, but carbon resistors are one of the oldest technologies, and they're still being used. And the schematic symbol looks like that, or sometimes like this. And again, units of a resistor are ohms. That's the symbol for the Greek letter omega. And the structure, the internal structure of a carbon resistor typically looks like this. The leads come in. These are the leads you see on the outside, and they're metal. And there are these little end caps inside that connect to the material that actually creates the resistance. And that material consists of carbon particles and graphite powder and ceramic powder in the appropriate mixture to provide the resistance that you want. And the resistance you want come in standard values. As a designer, you typically, you want certain resistances in your circuit to achieve certain functions. And you can pick from these standard values, like a 1 ohm resistor, a 100 ohm resistor, 24K. 47K shows up quite a bit in audio. You have your mega ohm. We just created a 1 mega ohm resistor downstairs. I think we created did we create a 6 mega ohm resistor? They come in standard values. And I'm not going to get into this in too much detail, but you can see there's a color code. There's a color code on resistors. Well, at least the old, not surface mount, the modern style, but the old style resistors. And that color code indicates the value. And if you want to study this slide, you can. I'm not going to get into too much detail because I'm not trying to teach you how to design things. But the point behind this is you can read these values and read these colors and determine the color code. And interestingly, not many people know this, but this color code is kind of, sort of derived after the rainbow. And if you remember Roy G. Biv, the name, Roy, red, orange, yellow, G, B, and there you have to put an I in there, you have to get a vowel in there, IV. To remember the rainbow, and that's kind of gives you the order of these things. Anyway, so And resistors also have a tolerance. They're never perfect. So, you know, if you're ordering up, if you pick a 220 ohm resistor out of your package there, it's not going to be exactly. If you're going to measure it with your ohm meter, it has a tolerance of plus or minus 5%. That means it could be 220 ohms, or it could be 225 ohms, or 215 ohms, plus or minus. It could be 5% above or below that 220 ohms. So, for example, I can't run 5% in my head of 220, but if it was a 100 ohm resistor, it could be 95 ohms through 105 ohms. Now it's time for a demo. And we're almost finished, and I always, to the extent that I can, I don't want you to believe me. I want to show you. So before I go to the workbench, I want to show you what we're going to do. I want to prove to you that this actually works in reality. And what we're going to do is I'm going to pick a resistor out of my kit. I don't even know yet what values I'm going to pick, but we're going to measure it first with an ohm meter. And I'm going to put a voltage across it. And I'm never going to change that voltage. So I'm going to do 3 different experiments. I'm not going to change the voltage. And I'm going to hook an ammeter up in series. And we're going to measure the current. Okay, this is step 1. We're going to measure the current. Whatever the current is, it is. This resistor is going to choose that current. Okay? We're going to figure out what that current is. Then we're going to put that's 2 resistors in series, the same value. Okay, we're going to maintain that same voltage across both of them. So we're going to have 2 times the resistance. So what should that do to the current if we have twice the resistance in a series circuit? Well, hopefully we should get 1/2 of the original current because we have twice the resistance. If you think about it intuitively, that's what should happen. If I have twice the resistance, I should get 1/2 of the current. Okay, so if you want to think of the water analogy, you know, I've got water flowing through here, and if I were to, you know, decrease that pipe size by 1/2, I should get about 1/2 of that flow. However you want to measure it. And then the third step we're going to do, I'm going to maintain that same voltage across the resistor, but I'm going to put 2 resistors in parallel. So what's going to happen is the current gets to flow in 2 different paths. So let's do the water analogy here. Okay, initially I had water flowing down. Let me draw it like this, through this pipe. I'm going to draw that same pipe, but now the water gets to flow through 2 pipes of the same diameter. So what should the current be up here this time? Well, it should be twice the amount of the original current that we had up here. It gets to flow through 2 different paths of the same value. Now, again, I'm maintaining the same voltage, the same pressure. So let's hopefully attempt to prove it, unless something goes horribly awry and the laws of physics get violated today, in which case I'll win a Nobel Prize. All right, let's go down there and make this happen for you. Then we'll wrap things up, and I hope that you enjoyed this lecture. All right, let's begin with a single resistor, and here it is. If you want to refer back to the color codes and try to figure out what value that is, I'll leave that to you for homework, but I've got it hooked up to my old friend, my digital voltmeter, and I have it in the kilo ohms measurement mode, and it's in the
200K range, so we're reading 46.4 kilo ohms. 46.4. Let's jot that down. All right. So given that we measured 46,400 ohms, or 46.4 kilo ohms, I am going to apply 10 volts across it. Let's run Ohm's law. So I should expect the current running through that to be 10 volts, because that resistor will drop 10 volts. So 10 volts divided by the resistance will allow 0.0002 amps to flow, which is 0.2 milliamps. That's what I expect to flow through that. So here's my experiment. I'm going to produce this circuit right here. So the voltage source, the battery, is going to be this DC power supply right here. And the positive side will be running through an ammeter. Alright, so that ammeter will essentially be in line right there, in series. It will have no effect on anything. It won't be a load of any kind. It won't drop any voltage. Okay, the output of the ammeter will come back around, will flow through the resistor. I'll talk about these in a minute. And back around into the negative side of our battery, or our power supply, which is right there. And what these leads are just simply, we're going to measure the voltage drop across the load, so I can show you that I'm always going to be, so those leads right there are going to go to a digital voltmeter. So I can show you that we're always going to be dropping 10 volts throughout this experiment. So let's go ahead, and I'm going to rotate this knob, start applying the voltage, but I don't care what this says. I want to know that I'm dropping 10 volts across that resistor. That's close enough. All right, so let's take a look at our ammeter. And we are reading 0.22 milliamps. So we can round that down. That's 0.2 milliamps. And what did I expect? 0.2 milliamps. All right, now we're just simply going to add a resistor in series. And I would expect, just like I told you, if I add a resistor in series there, I would expect that current to drop by 1/2 to 0.1 milliamps, because I've doubled the resistance. Well, let's try it. All right, I've got two of the same value resistors in series. So I should be doubling the resistance to the flow of current. I'm going to maintain same voltage, 10 volt drop. So the 10 volt drop is across both of them, so we have the same pressure. And let's see how much current is flowing through. We've dropped down to 0.1 milliamp, just like we expected. Now, just like I discussed before, let's put these two resistors in parallel instead of in series. And if in that case, we would expect this 0.2 milliamps to double. So what's 0.2 doubled? It should be 0.4. milliamps. Let's find out. Okay, there's our two same value resistors in parallel. I'm maintaining 10 volts across them. And what do we have here? 0.4 milliamps. Just as expected, no laws of physics were violated today. Everything went as planned and as expected. So now you can see it works. Stereo Police, I hope you have enjoyed this lecture. There are more to come. It's New Year's Day 2024. Hope you have a wonderful new year. I'll see you again real soon. Ciao.